At 5:37 in the afternoon, on August 29, 1907, the largest bridge in the world fell into the St. Lawrence River. 86 men were on the structure. The end-of-shift whistle was 8 minutes away. 15 seconds later, 19,000 tons of steel and 75 workers hit the water. The consulting engineer who designed it was 500 miles away in New York. He had never visited the construction site, not once in 4 years. The telegram he sent that morning to stop all work arrived at the office while the chief engineer was out to lunch. 9 years later, they rebuilt the bridge, and it collapsed again. This is the full story of the Quebec Bridge, the deadliest bridge construction disaster in history, and the engineering failure so devastating that every Canadian engineer still wears a steel ring on their working hand because of it. Quebec City, the 1850s. The St. Lawrence River was nearly a mile wide at its narrowest crossing point, fast-moving, choked with ice flows for months every winter. During summer, the only way from the south bank to the north was by ferry. Once winter set in and the river became impassable by boat, everyone waited for the water to freeze solid. Then they established an improvised ice bridge for wagon crossings. It was dangerous, unreliable, and people died on it regularly. Local politicians and businessmen had been talking about a permanent bridge since the 1850s, but the width of the river and the depth of the water made the project seem impossible for the available technology. That changed in the 1880s, when Cantilever bridge design proved it could span distances that suspension bridges and simple trusses could not. The Forth Bridge in Scotland, completed in 1890, stretched 1,700 feet across the Firth of Forth. If Scotland could do it, Canada could do it bigger. In 1887, the Canadian Parliament passed an act incorporating the Quebec Bridge Company. But here is where the problems started. The company had almost no money. Government funding requests were declined repeatedly because no one had even selected a site yet. Years of political debate followed. The man who eventually drove the project forward was Simon Napoleon Parent, who served simultaneously as Premier of Quebec and President of the Quebec Bridge Company. That conflict of interest would haunt the project, but at the time, nobody raised concerns. By 1897, the company finally had preliminary site surveys completed and a modest budget approved. They needed a chief engineer. They hired Edward Hoare, a Canadian railway engineer who had worked on bridges his entire career. The Royal Commission would later reveal a devastating fact about Hoare. He had never worked on a bridge longer than about 300 feet. The Quebec Bridge would be 1,800 feet. That was 6 times beyond anything in his experience. But Hoare was affordable, and the Quebec Bridge Company was running on a shoestring budget. Hoare needed help. The company brought on Theodore Cooper as consulting engineer. Cooper was 65 years old, operating out of a small office on West 29th Street in New York City. He was considered one of America's foremost bridge engineers. He had designed the Cooper E loading standard that railroads across the continent still used. He had worked on elevated railroads in New York and was twice awarded the Norman Medal from the American Society of Civil Engineers. For Cooper, the Quebec Bridge was meant to be the crown achievement of his career, the largest cantilever span ever built, surpassing even the Forth Bridge. His name would be on it forever. Cooper made a critical decision early in the process. The original design called for a main span of 1,600 feet. Cooper extended it to 1,800 feet. A longer span meant fewer piers in the river, which reduced costs. It also meant the Quebec Bridge would be the longest cantilever in the world by 100 feet. Cooper's ego and the company's budget both benefited from that decision, but lengthening the span by 200 feet dramatically increased the load on every single structural member in the bridge. The contract for the steel superstructure went to the Phoenix Bridge Company of Phoenixville, Pennsylvania. Phoenix was famous for its patented Phoenix column, a built-up cylindrical section used in bridge construction across America. But Phoenix had limited experience with cantilever spans of this magnitude. Their bread and butter was a series of simple span trusses. The designing engineer at Phoenix was Peter L. Szlapka, a Polish-born structural engineer who created the detailed drawings for every member in the bridge. Szlapka designed the lower compression cords of the anchor arm as built-up latticed columns. 4 ribs, each assembled from 3 steel plates, 54 inches wide and 15/16 of an inch thick, plus a narrower plate at 37 3/4 inches. The ribs were connected by stitch rivets and lattice bracing, with a total cross-sectional area of 781 square inches. The compressive load between abutting cord segments was supposed to transfer entirely through carefully milled end-bearing surfaces. The joints were butt-jointed, not pin-connected, and not continuous. These cords were the backbone of the entire structure. Everything depended on them carrying the compressive load without buckling. In 1905, during construction preparations at the Phoenix Bridge Company yard in Pennsylvania, the cord designated a 9L was dropped during handling and bent. Phoenix workers straightened it, declared it repaired, loaded it onto a rail car, and shipped it to Quebec. Nobody questioned whether a cord that had been dropped, bent, and straightened was still fit to carry the compressive loads of the largest cantilever bridge in the world. That same cord, a 9L, would be the first member to fail 2 years later. When Cooper extended the span from 1,600 to 1,800 feet, Szlapka prepared the redesign. But Phoenix never fully recalculated the dead weight of the longer bridge. They detailed the south anchor arm based on the old 1,600-foot dead load assumptions. Cooper later checked the arithmetic, found stresses were about 7% higher than designed, and decided that 7% was, in his own words, not a fatal increase. He told the Royal Commission there was no remedy at that point. The Royal Commission, however, determined the actual weight increase was closer to 18%. Cooper had also raised the allowable working stresses to 21,000 pounds per square inch under standard loading, at a time when 16,000 pounds per square inch was the accepted industry maximum. And he had reduced the design wind pressure from the fourth bridge standard of 56 pounds per square foot down to just 30. Every safety margin in the original design was being squeezed from multiple directions simultaneously. If you have been following this channel for a while, you know that the difference between 7 and 18% in structural engineering is the difference between a safe bridge and a death trap. Like and subscribe if you want the full breakdown of what happened next, because the construction equipment on this project was unlike anything else being used in 1907. The Phoenix Bridge Company did not simply lift the Quebec Bridge into place with conventional derricks. They designed what was, at the time, the largest moving electric crane ever built for a bridge construction project. Contemporary press called it the Gigantic Traveler. It sat 210 feet above the bridge floor, which meant the top of the crane was more than 360 feet above the surface of the St. Lawrence River. The entire rig was electrically driven. In 1905, when steam-powered erection equipment was still standard on most major construction sites in North America, Phoenix was running an all-electric Traveler crane on rails set outside the extreme width of the bridge. It used over 15 miles of wire rope in its rigging and could command every piece of metal entering the structure. The Manitoba Free Press described the motive power as entirely electrical and reported that its operation had been very successful. If you have watched our documentaries on the machines that built the Golden Gate Bridge or Hoover Dam, you know that erection equipment often defined the pace and the risk of an entire project. The Quebec Bridge Traveler was no different. Before shipping it to Quebec, Phoenix built a complete working scale model of the entire bridge inside their Phoenixville shop, solely to test the crane's movements and clearances. That level of pre-erection mock-up testing was virtually unheard of for the era. The model allowed Phoenix engineers to rehearse the sequence of steel placement before a single beam left the fabrication yard. There was also a smaller second traveler built specifically to erect one half of the suspended span outward from the cantilever tip. This is the rig visible in the famous final photograph taken on August 27, 1907, 2 days before the collapse. The small traveler sits on the left side of the frame, the gigantic traveler at the far end of the cantilever arm, and the St. Lawrence stretches below. In addition to both travelers, crews used a separate hanging work platform called the Flying Bridge. This rig was suspended below the bridge deck on cables and allowed riveting gangs to hold bottom cord members in position from underneath while bolting them into place. The Flying Bridge is almost never mentioned in accounts of this disaster, but it was a genuine engineering innovation for its time and gave crews access to connection points that would have been impossible to reach from above. A working locomotive ran out on the partially completed bridge deck to deliver steel members directly to the erection crews at the cantilever tip. On the afternoon of the collapse, that locomotive had just delivered an 8-ton load and was heading back for another. One of the survivors, a man named Thomas Sewell, was working on the gigantic traveler over 200 feet above the deck when the bridge fell. Newspaper accounts from August 30th described his escape from the collapsing traveler as little short of miraculous. Construction of the substructure began in 1899 under contractor M.P. Davis of Ottawa. The massive concrete piers were finished by 1902. The Phoenix Bridge Company began erecting the steel superstructure on July 22, 1905, working outward from the main south pier. Phoenix had a hard penalty clause in their contract: $5,000 per month in liquidated damages if the bridge was not complete by December 31, 1908. That deadline created constant pressure to keep steel going up regardless of conditions. By the summer of 1907, the south anchor arm was complete, the south cantilever arm was extending out over the river, and the first 3 panels of the suspended span were already in place. The bridge was almost halfway across the St. Lawrence. And then, the warnings started coming in. Norman McClure was a Princeton graduate in his late 20s. Cooper had hired him as the on-site inspector, his eyes and ears in Quebec. Starting in June 1907, McClure noticed deflections in several lower cord members that looked wrong. He reported bent cords on August 6th. Cooper wired back a message that was almost plaintive. He asked how that had happened. McClure reported 2 more bent cords on August 12th. John Sterling Deans, the chief engineer of Phoenix Bridge, insisted work continue. Cooper, grasping for an explanation from his New York office, telegraphed McClure a theory. Maybe the cords had been struck by suspended beams during erection. He told McClure to look for evidence of impact. McClure investigated and found no evidence of any such blow. On August 27th, McClure remeasured cord 9L of the anchor arm. He measured the specific member that Slapka had designed with those 781 square inches of cross-section. 1 week earlier, one rib had been 3/4 of an inch out of alignment. Now it was 2 1/4 inches. The deflection had tripled in 8 days. McClure wrote to Cooper that the present shape was undoubtedly due to the stress the cord was receiving. Construction foreman E.R. Kinloch halted work on August 27th. This was the moment the bridge could have been saved. But the next day, Edward Hoare intervened. Hoare warned Cooper that the moral effect of stopping work would be very bad on all concerned and might stop construction for the entire season because they would lose the workers. There had already been a strike earlier that summer. Crews were depleted. Work resumed on August 28th. On the morning of August 29th, McClure took the overnight train to New York and reached Cooper's office. Cooper finally grasped the severity of what McClure was describing. At 12:16 p.m., Cooper dictated a telegram to Phoenix Bridge that read, "Add no more load to bridge till after due consideration of facts. McClure will be over at 5 o'clock." The telegram arrived at the Phoenix offices in Phoenixville, Pennsylvania at 1:15 p.m. But John Sterling Deans, the one man with authority to stop construction, was out of the office. He did not return until about 3 p.m. He read the telegram, but decided to wait for McClure to arrive before taking action. McClure reached Phoenixville at 5:15 p.m. The executives met briefly and agreed to discuss the matter in the morning. At that exact moment, 500 miles north in Quebec, the bridge had already been in the river for 38 minutes. You are hearing that correctly. The meeting to decide whether to stop construction was still happening while the structure was already gone. The telegram that could have saved 75 lives sat on a desk for nearly 4 hours, while the chief engineer was at lunch. At 5:37 p.m. Eastern Time on August 29, 1907, cord a 9L buckled. The compressive load instantly transferred to A9R on the opposite side of the bridge. A 9R buckled seconds later. The entire south anchor arm, the south cantilever arm, and the 3 panels of the suspended span that were already erected collapsed into the St. Lawrence River. 19,000 tons of steel fell in approximately 15 seconds. The sound was heard 10 kilometers away in Quebec City. Residents thought it was an earthquake. Like and subscribe, because what happened to the community of Kahnawake in those 15 seconds is one of the most devastating stories in North American construction history, and we are going to tell it properly. 86 workers were on the bridge when it fell. 75 died. 11 survived. Only 16 bodies were ever recovered from the wreckage, and multiple accounts describe those bodies as badly mutilated, some severed in half. The remaining 59 workers were entombed in the twisted steel on the riverbed. Of the 75 dead, 33 were Mohawk ironworkers from the Kahnawake Reserve near Montreal. Kahnawake had sent 38 men to work on the Quebec Bridge. They lost 33 of them. That is roughly 87% of their entire contingent, gone in 15 seconds. The Mohawk ironworkers had not come to high steel work through the Quebec Bridge. That tradition started 2 decades earlier, in 1886, when the Canadian Pacific Railway built a cantilever bridge across the St. Lawrence near Kahnawake. The Dominion Bridge Company had offered the Mohawks day labor jobs in exchange for putting a bridge abutment on reserve land. The Mohawk workers, who were river pilots and quarrymen by trade, kept climbing the growing steel structure to watch the ironworkers. A Dominion Bridge supervisor later wrote that they were as agile as goats and immune to the noise of riveting that usually made newcomers sick and dizzy. Within a few years, Kahnawake had produced some of the best bridge ironworkers on the continent. Tradition held fast. The Delatte family alone lost 7 men in the collapse. 4 brothers, an uncle, a cousin, and a brother-in-law. Those 7 deaths left 22 fatherless children. The widow of Joseph Orit de Delatte was pregnant with their 11th child when her husband fell into the St. Lawrence. 7. Lives from one family were gone. Across the entire community, 25 women became widows, and 53 children lost their fathers. Kahnawake's only telephone was in the post office. It rang at 6:30 p.m., 53 minutes after the collapse. Postmaster Antoine Glasson ran into the street with the news. Word spread house to house through a community of about 2,000 people, where every single family knew at least one victim. The Mohawk language word for the disaster is Shontosquen. Widows and children grieved together. 6 Mohawk workers survived. One of them was Alexander Beauvais, a riveting gang leader who had reported broken rivets and bending ribs to his supervisor, C.R. Meredith, only 30 minutes before the collapse. Meredith told Beauvais it was not serious. Meredith died in the collapse. Beauvais was inside a cord driving rivets when the bridge fell. He wrapped his arms and legs around the steel and rode it down into the river. He broke one foot and his nose. He would later become a Dominion Bridge Company superintendent and personally erected the steel memorial crosses at each end of Kahnawake using donated steel girders. Beauvais survived and later helped remember the dead. A third memorial cross in the Kateri Catholic Cemetery, distinct because it is of riveted construction, was reportedly assembled from pieces of the actual collapsed bridge wreckage. 6 other Mohawk workers survived that day because they had quit at noon after a dispute with their foreman. 30 of their kinsmen were on the bridge when it fell that afternoon. Memorials stand where lives were lost. The Canadian government appointed a royal commission the morning after the collapse. 3 engineers were named: Henry Holgate of Montreal as chairman, John Galbraith as Dean of Applied Science at the University of Toronto, and J.G.G. Carey of McGill University. They held hearings in Quebec City, Ottawa, New York, Philadelphia, and Phoenixville between September and November 1907, with additional sessions running into January 1908. They hired C.C. Schneider of Philadelphia as their independent technical reviewer. Schneider ran full-scale destructive compression tests on replicas of the failed cord members at the Phoenix Iron Works. The lattice bracing connecting the 4 ribs failed explosively when the rivets sheared, followed immediately by buckling of the individual ribs. The cords could not act as a single structural unit under load. That was the fatal defect. Schneider wrote that the latticing was not sufficient to make the parts composing them act as a unit, and that the most pronounced defect in this respect existed in the lower cord members of the cantilever and anchor arm. The commission also uncovered a buried detail. A government bridge engineer named Robert C. Douglas had opposed Cooper's calculations years earlier. Douglas was effectively removed from the project on July 9, 1903, because of his objections. The cabinet sided with Cooper and shut Douglas out by August 15th. The one man inside the Canadian government who had the technical knowledge to challenge Cooper's numbers was silenced before a single piece of steel was erected. The commission's 15 conclusions were devastating. The collapse resulted from defective design of the lower cords. The design was made by Peter Slapka. It was approved by Theodore Cooper. The failure cannot be attributed directly to any cause other than errors in judgment on the part of these 2 engineers. Perhaps the most damning sentence in the entire report was this: "It was clear that on that day the greatest bridge in the world was being built without there being a single man within reach who, by experience, knowledge, and ability, was competent to deal with the crisis." The report also stated plainly that the professional knowledge of the present day concerning the action of steel columns under load is not sufficient to enable engineers to economically design such structures as the Quebec Bridge. Cooper's own testimony was chilling. He admitted he had accepted Slapka's work to some extent, upon faith in Slapka's ability, because he was unable to give matters the careful study that it was his duty to give them. When pressed on whether engineering knowledge was sufficient for this kind of structure, Cooper deflected. "My responsibilities, gentlemen, end as soon as the truth is reached." No criminal charges were filed against anyone. Cooper simply retired. Slapka continued working at Phoenix Bridge and faded into obscurity. The Canadian government took over the project and created a board of engineers under Lieutenant Colonel Charles Montserrat. They brought in Ralph Modjeski, the Polish-American engineer from Chicago, who would later design the Benjamin Franklin Bridge. The contract went to the St. Lawrence Bridge Company, a joint venture of Dominion Bridge and the Canadian Bridge Company, with chief engineer George Herrick Duggan leading the redesign. everything changed. The new bridge used nickel alloy steel rolled by Carnegie Steel in Pittsburgh, allowing dramatically higher allowable stresses without buckling. It introduced the K-truss bracing system, invented by St. Lawrence Bridge Company president Phelps Johnson, in a major bridge for the first time anywhere in the world. The replacement bridge weighed roughly 2.5 times as much as Cooper's original design, and the contract placed entire responsibility for design adequacy on the contractor, regardless of board approval. That clause was written specifically because of the finger-pointing that followed 1907. Like and subscribe, because the story of this bridge was not over. 9 years after the first collapse, the St. Lawrence was about to swallow another span. Rather than building the suspended span outward from the cantilever tips, the way Phoenix had attempted, the new engineers decided to prefabricate the entire center span on land at Sillery Cove, about 3 miles downstream. They would float it on barges, tow it to the bridge site, and hydraulically jack it up from the ends of the cantilever arms. The center span weighed approximately 5,000 tons and stretched 640 feet. It was assembled between May and July of 1916. On the morning of September 11, 1916, the operation began. At 3:40 a.m., the span was floated at Sillery on flat-bottomed scows. By 6:35 a.m., it reached the bridge site. By 8:50 a.m., hydraulic jacks began the lift, and by mid-morning the span hung about 20 feet above the water. The scows floated clear. Hundreds of spectators lined both banks. Photographers documented what everyone believed would be the moment the Quebec Bridge was finally made whole. At 10:50 a.m., a sharp crack echoed across the river. A cruciform-shaped steel casting at the southwest corner of the span fractured. Each of the 4 corner castings was carrying approximately 1,200 tons. When the southwest casting failed, the corner dropped, the span tilted, and the entire 5,000-ton center section slid off its supports and plunged back into the St. Lawrence. 13 workers died. The wreckage settled on the riverbed directly beside the 1907 debris. The St. Lawrence Bridge Company accepted full responsibility in writing within 2 days. A remarkable contrast to the years of blame shifting that had followed the first disaster. Engineer Franz Lichtenberg had warned about problems with the castings 6 weeks before the lift. His warnings, like McClure's 9 years earlier, had not been acted on quickly enough. The new suspended span was fabricated in less than 3 months during the summer of 1917. It was floated into position on September 17th. The entire lifting apparatus had been redesigned. The cruciform castings that required rotation about 2 axes were eliminated entirely, replaced by a simpler mechanism that removed the second pin responsible for the original bearing type. At 4:01 p.m. on Thursday, September 20th, 1917, the 10-inch pins connecting the suspended span to the cantilever arm ends were driven home. The Quebec Bridge was complete. The first train crossed on October 17th. Regular rail traffic opened on December 3rd, 1917. The Prince of Wales formally dedicated the bridge on August 22nd, 1919. The final cost was approximately $25 million, against an original budget of $8 million. Theodore Cooper died of pneumonia on August 24, 1919, at his apartment in New York City. He was 81 years old, unmarried, and had never built another bridge after the disaster. He died less than 4 months before his bridge officially opened for regular traffic. There is a famous story that every Canadian engineering graduate receives an iron ring forged from the wreckage of the Quebec Bridge. We spent considerable time researching this, and the truth is more interesting than the myth. The iron ring tradition is real, but the rings were never made from bridge wreckage. The ceremony was proposed in 1922 by Professor Herbert Haultain of the University of Toronto. In 1923, Haultain wrote to Rudyard Kipling the Nobel Prize-winning author of The Jungle Book, and asked him to compose a ritual for graduating engineers. Kipling responded enthusiastically and wrote the obligation of the calling of an engineer, including the line, "Let all who build beware." The first ceremony was held on April 25, 1925, in Montreal. That was 18 years after the 1907 collapse. The original rings were hand-hammered by World War I veterans in Toronto from ordinary wrought iron, not from bridge steel. The rings were deliberately made with a rough outer surface that catches against paper when you write or draw, serving as a constant physical reminder of professional responsibility. The connection to the Quebec Bridge is moral, not material. Halton's motivation was specifically the hubris of Cooper and Slapka, the deference to authority, and the refusal to revisit calculations that had killed 75 men. The real legacy of those 15 seconds in 1907 was carried not by iron rings, but by the Mohawk women of Kahnawake. After the disaster, the women held a council through Kahnawake's matrilineal governance structure and made a decision that would shape North American construction for the next century. Never again would a large number of their men work on the same project at the same time. The men had to scatter across the continent, taking jobs at different construction sites in smaller crews. They called it booming out. The decision was painful but practical. By 1916, the American Board of Indian Commissioners reported that 587 of the 651 men on the Kahnawake Reserve were members of the Structural Steel Union. The 1927 federal court ruling, citing the Jay Treaty of 1794, confirmed that Mohawks could pass freely between Canada and the United States for work. That legal precedent turned the booming out practice into a permanent cross-border labor migration. Mohawk ironworkers settled in Brooklyn, New York, in a neighborhood around 4th Avenue and Atlantic Avenue that they called Little Caughnawaga. At its peak in the 1960s, about 800 Mohawk ironworkers and their families lived there. They were anchored by Local 361 of the Ironworkers Union. A bar on Atlantic Avenue called the Wigwam had a sign over the entrance that read, "The greatest ironworkers in the world pass through these doors." A local Presbyterian minister named David Monroe Corey actually learned the Mohawk language so he could give sermons to his ironworker congregation. Mohawk crews worked on the Empire State Building, where the last piece of structural steel was placed by a Mohawk worker on September 15, 1930. They built the Chrysler Building, Rockefeller Center, the George Washington Bridge, the Verrazzano Narrows Bridge, and both the original World Trade Center towers and the replacement Freedom Tower after September 11, 2001. In 2015, the United States Mint issued a $1 coin honoring the Kahnawake and Akwesasne Mohawk ironworkers. If you have watched our documentary on the machines that built the Empire State Building, you have already seen the work of men whose fathers and grandfathers fell into the St. Lawrence on that August afternoon. The tradition that started with a railway bridge in 1886, that was devastated at the Quebec Bridge in 1907, and that was preserved by the women of Kahnawake through the booming out decision, is still alive today. Approximately 200 Kahnawake ironworkers still make the weekly commute from the reserve to construction sites in New York City. The Quebec Bridge still stands today. It remains the longest cantilever bridge span in the world at 1,800 feet. It carries 3 highway lanes, 1 rail line, and a pedestrian walkway. In 2015, the National Trust of Canada placed it on the list of the 10 most endangered historic sites in the country, with roughly 60% of the bridge surface covered in corrosive rust. In May 2024, Canadian National Railway sold the bridge back to the federal government for a symbolic $1, and the federal government committed $1 billion over 25 years for repairs and maintenance. The fallen wreckage from both the 1907 and 1918 collapses has never been removed. It still sits on the bottom of the St. Lawrence River, directly beneath the bridge deck. Every train and every truck that crosses the Quebec Bridge passes above the steel remains of 88 construction workers. If you found value in this documentary, please like and subscribe. That helps us keep telling the stories that the construction industry has tried to forget.